Hello and welcome to the screencast on using R to generate Monte Carlo confidence intervals for simple linear models, simple linear regressions. In the previous screencast, we discussed the basics of performing Monte Carlo simulations, but we didn't get as far as saying, well, what if we actually have data? We're still going to stick today with simulated data that has a couple of useful properties, but in the screencast to follow this one, we'll start working with real data, which has all of the sort of standard problems that one has to deal with more complex real biological data. So very simply what we're going to do is we're going to simulate some fake data as if we're fitting a regression. So we're going to assume we have some predictor variable, our x here, that goes from -10 to 10, and that's our covariate, where we assume we know these are known values. And the deterministic parts of this model, we are just going to do a simple linear regression, so we're just going to essentially fit lines. And our intercept's actually going to be 0, and our slope will be 1.5. So we'll run those. And then we're going to generate some data. And this is our y, and we're just generating some amount of variation. For the purposes of this screencast, think of this vector y as the observed values of our response. This is what we had collected. We had collected this y data, and x was determined before, maybe dose response or something similar, something measured with relatively low error. Of course, we can plot the relationship of y and x as we should. Nothing particularly spectacular there. We'll come back to that later. And we, of course, will start, as we often do, by perhaps fitting a simple linear model. So we just fit a linear model to it, and we can look at the coefficients of that and the confidence intervals of that model here. And we have an estimate. The estimate's actually not given what we sort of know what the estimate should intercept should be. We see that our estimates are not particularly good. It's not a large sample size, so perhaps not so surprising. And even our slope, although it certainly is, well, does our slope even include our true value? Nope, our slope goes from 0.05 to 1.34. So we're close, but doesn't quite include it. So this is clearly showing you, with small data sets, your samples can sometimes be odd, but let's work with it. And we can look at the covariance between parameter estimates, and this is sort of an important point here. You'll notice that there's no covariance between the slope and the intercept. I want you to think a little bit about why. We've discussed this in previous screencasts and lectures, and so on. And of course, we'll because we like to visualize things, we can plot the best fit line onto that data. Okay, well, nothing new there. So what we're going to start with before we actually generate the confidence intervals using Monte Carlo, we're going to, and I've discussed this before, so I won't go through all the notes here, but we're just going to use the asymptotic normal confidence band. So essentially just using pretty much what you would get if you used the predict function here to construct the confidence bands around the observed data. And I'll let you read up on this if you've forgotten in the script itself. But the important parts is that we first of all have to generate a data frame with our predictor variable, and our predictor variable's name is x, and for this data frame the name of the predictor here needs to be the same as in the actual model we're using. So we'll just call that x.frame, and our x value will just be equal to x, because that's what we called it. What's most important here is to remember that the values of our predictors need to be sorted, or else you'll have some real problems. What we'll then do is use the predict function to generate confidence intervals. We'll just use the conf_int function, and we'll just call predict, and essentially we're predicting from the model we fit, lm.1, given the data that we're using to predict is that x.frame, our values of x, which was in this case just our actual values of x that we use, which was from -10 to 10, and we are asking for intervals equals conf. And that will give us the confidence intervals, which includes both the best estimate, which will be same as just the fitted line, and the bands, 95 upper and lower bands. You can also use the prediction intervals instead of the confidence intervals. Those, of course, can be wider because it's for predicting future observations, but that's not our goal here. So let's just run that line. And we can just take a quick look at what we see here. And so this is going to give us our fitted line. So for each value of x, this would be the fitted estimate, and the lower and the upper values, and that would increase for all 20 of these values. And what we'd want to do is plot these lines, and we could just plot this fitted line and then lower line and upper line, easy enough. We just call lines 3 times. Instead, we're going to use something a little bit more convenient called matlines, or matrix of lines function, where we say, our x values that we want to do, because it'll only be one x, is just x.frame at $x. So we're just grabbing the variable x in that data frame. And the different y values, the ones that we're going to want to plot multiple lines for, are the ones that we just generated these confidence intervals for, this conf.int set of lines. And then we can specify the line types, thickness, and whatever, or colors just as vectors. Here we'll just keep them all red, and we can take a look at what that looks like. And indeed, exactly as we expect. Okay, now we'll actually go ahead and do the generation of the Monte Carlo simulations. So first we're going to do a simple one, and we're specifically going to ignore a couple of things which we will have to consider later on, but I want to sort of help build the intuition of what we're doing, and what we're not going to account for this one is uncertainty and residual variation. So we're going to generate simulated values, but there's certain aspects of the way we're going to do the simulations that are going to lead to somewhat, the confidence intervals will be too narrow. We'll talk, and you should think about what is missing as we go through this. And so what I've done, and let's go through this function so you can see what's going on. I've written a simple function, simreg1, and as the input is just the actual model we're using. And right now it's written specifically just for sort of a very simple model with a single predictor. And what it's going to do is extract from that model that you give it. By default it goes to lm1, lm.1, but you could change it to whatever. It's going to take out the intercept and the slope of the model, a and b. And then it's also going to take out the residual squared error, residual standard error of the model. So that's all of the variation that was unaccounted for by the model. And we're going to use that to actually build our simulation. So what we're going to do is we're going to generate new values of our response variable, and this is very important. So we're generating new values of our response. And the way we're doing that is in this case, we're going to simulate from a normal distribution. But obviously you can do it for any distribution you want. And we're going to simulate how many observations are we going to simulate? We're going to simulate the number of observations basically equal to the number of predictor observations we have, which I think is 19 or 20 here. And the model we're going to fit is a line with a plus b times x, right? And that's just going to be our best estimate of a here and our best estimate of b that we estimated from the model. And then the amount of variation that we're going to generate in the response variables is going to depend on the residual standard error from the model. So essentially we're using the unexplained variation from the model as the amount of variation we should be incorporating. As you'll see as a first blush, this works reasonably well, but it will be a little too narrow. Then what we do is we take the simulated values for y.sim, and we're going to run a linear model where we use y.sim, but with our original x. So we're not simulating new values of x. We certainly could, and there's some ways of doing that. But here we're going to use the values of x. We're just simulating new response variables and fitting them back onto the predictor variables, which was a vector from -10 to 10. And from all of that, we'll just pull out the slope and the intercept, the coefficients, after performing the simulation. And so this is just simreg1. We run it, we can clear that, and we can call it over and over and over again, and we will get our various estimates. Of course, that's a pretty not high throughput way of doing something. So what we'll do is we're just going to say, well, let's do 1,000 simulations. We'll make big N equals 1,000, and we'll use the replicate function as we discussed in some detail in the previous screencast. And so we're just going to generate a matrix here using replicate so that we have a matrix where we're getting the slope and the intercept for each simulation, and we'll do that simulation 1,000 times. So we should get a matrix that has 1,000. It actually defaults to 1,000 columns and 2 rows, but we'll change that around to make it a little bit easier. And what we'll do is run it, doesn't take very long, and we're just going to change it so that we end up with 1,000 rows by 2 columns, with the first column being the intercept, second column being the slope. And again, we can look at this head of simulated coefficient, and what we'll see is estimates for the intercept, estimates for the slope, and these are the first 6 of 1,000. And we can use this to look at, get estimates of the standard error, and simply all we need to do, and you should think about why at this point, you should hopefully be quite familiar why this will work, but if we looked at the standard deviation of the simulated intercepts, which is simulated.coef, the first column of that, it's about 1.88. We do that same thing for the slopes, which is just going to be the second column, and we get about 0.31. We compare it to our estimates here, the standard errors from our estimates of the original model, which was about 0.308 for the slope, very close to 3.1, and about 1.86 for the standard error for the intercept, which is very much in the same ballpark as we see. So you should be able to understand why. We've discussed this a couple of times, and if not, please come ask me. Of course, we can generate approximate 95% confidence intervals, and the way we're simply just going to do this is from all of the 1,000 simulations we're going to do, we're basically going to say, hey, we're interested in sort of the cutoffs, the 25th or the 2.5% cutoff and the 97.5th cutoff. So basically, you could plot the histogram, make two lines at 2.5% and 97.5% of all of the simulated values, and that would be your approximate 95% confidence intervals using Monte Carlo simulation. It's that simple, so we're just using quantile here, just for the slope, and saying from the 2.5% to 97.5%. And let's compare them to the asymptotic confidence intervals here. And what you see is that we go from about 0.05 to 1.34 for the asymptotic ones, and they're a little bit different, 0.089 to 1.29, but by and large the coverage is pretty similar. Although in general, I'm not sure if it's going to be true in this particular case, in general the coverage will be small, or the range will be narrower for the way we just did the simulation than the asymptotic. So it's a little too anti-conservative. It's not quite accounting for all the uncertainty we have, as we will shortly see. And of course, as we're doing with any models, we always know to take a look at how the estimates are correlated with each other. We saw before that from the original linear model there was no correlation, and that's more or less what we would expect to see. And it's quite small. The correlation between the simulated slopes and simulated intercepts is only about 0.04, 0.05, tiny amount. And you can of course plot that if you really want, and basically see no relationship, which is good, which is what we would hope for. Of course, in many cases we won't have such a situation like that. Okay, and it's worth pointing out that I did this on purpose, and I'd like you to sort of think back early in the simulation what I did to make our lives easier with respect to keeping the intercept and slope independent of each other. Okay, so we'll actually now replot this and just make a plot that helps us give a good idea. And so we'll just first plot y and x. And then what we'll do here is we're just going to write a for loop, and we're just going to plot the first 95 simulated values for the intercept and slope. So I equals 1 to 95. So each row is a different simulation. So we're going to go from row 1 to row 95 and use the estimate of the intercept and the estimate of the slope in each of those cases. Of course, times x here, because we need to include the x values. And we'll just have public scripts. So one thing that's worth thinking about is, why am I only plotting the first 95 of the 1,000? Why not plot all 1,000? Other than it'll take a little while. So these are the first 95 lines we'd expect in gray that are from the simulations, and here are our confidence intervals. And you see that against the coverage is pretty similar, not exact, but pretty similar, and certainly giving you a pretty similar range. Okay, well that's pretty useful. The unfortunate thing in what we've done is we have, and as I've alluded to, we haven't actually accounted for the fact that our residual standard error actually has uncertainty as well associated with it. It's not a value that was known beforehand. It's essentially estimated from the data, just like everything else. So we need to incorporate uncertainty in that. So essentially we're going to have to, first of all, simulate variation in the residual standard error, and then use that to do our general simulation of the response variable. And so what we're going to do is just slightly modify the function we wrote above. We're still going to have RSE be the residual squared error, but now we actually have to include a couple other things, in particular the degrees of freedom, the residual degrees of freedom of the model. So how many degrees of freedom do we have left, essentially, after we fit? And we only fit one per the intercept and the slope. Those are only parameters. We have not had, it wasn't a very complicated model, but it was also a small sample size. And we're going to have just really two more lines and a slight modification of one more. We're going to add a variable to store the degrees of freedom, df.sim, and then we're going to store a variable to generate the residual standard error, the simulation for the residual standard error, incorporating the uncertainty. So the first few lines are the same. We're just grabbing the model. The input's exactly the same with this one. These first two lines are identical as above. Here we've just added a line to basically pull out from the model the number of degrees of freedom. And here's the residual squared error, just like before, nothing different there. Here's the line that has everything that's different to understand what's happening. And what we have here is our RSE right here, as before, and that's a residual squared error. And this whole term, what we're doing here is basically this is what's allowing us to add uncertainty, or rather incorporate the uncertainty by simulating the changes in the variance we would expect for the residual squared error. And this is gone into in a great deal of detail in Gelman and Hill. And it's already been, I've already asked you to read about it. Essentially what it's going to do is produce a ratio of the number of degrees of freedom you have over essentially a simulated number from that kind of distribution. And that ratio, when your degrees of freedom get very, very large, it's going to always be very close to 1. So the square root of that whole, well, the square root of essentially something close to 1. With smaller numbers, that number will bounce around a lot more, and that can make the residual squared error larger or smaller depending on it. So allowing us to account for uncertainty into it. And then otherwise, everything else is exactly the same. We then use this new RSE sim value. So under each simulation, we generate a new residual squared error, or residual standard error, sorry, and then use that to generate our simulated response, and then fit our model just as we did above. So we can call that. And then just do exactly as we did before. We can look at replicate. We use replicate here again. Just run them. Doesn't take too long, maybe a minute or so. And then we can. I think I erased the other plot from before. So let's just add the. Here was the original plot that we had. Let's just go down and add the new estimates right here. And these should be in blue, and you'll see them. And it's sometimes hard to tell, but there is generally going to be a little bit more spread. This is perhaps not the easiest way of seeing that additional spread. So instead, what I suggest, if you want to take a closer look, is compare the estimated Monte Carlo confidence intervals where we've adjusted for uncertainty in the standard error, this first one, versus the Monte Carlo confidence intervals where we didn't adjust for variation in standard error, and then of course our asymptotic normal confidence intervals. And I'll let you do that. And you can sort of look at the range and exactly where they extend to. And in any given simulation, it might be hard to see the differences, but in general, you will notice that the where you account for the uncertainty in residual standard error, those will tend to be broader confidence intervals and more in line generally with the asymptotic normal. Okay, and I do want to make the point before we finish, only another minute or so of this, is that we have not yet accounted for covariation among parameter estimates, and we will cover that in one of the next screencasts. There's a couple of other alternatives if people don't like using the replicate function, especially if you have to do tens of thousands or millions of simulations. Using a for loop can be a more effective method. It's very straightforward to do it. We really don't have to change very much. All we're going to do here is first initialize a matrix to store all our future simulated values for slopes and intercepts. So we're just calling a matrix, filling it with a bunch of missing data, NAs, saying, well, we want 2 columns, one for the intercept and one for the slope, and our number of rows is just going to be big N, which at the moment I think is 1,000. So we run that. And again, if you look at that matrix at the moment, it's going to be, probably should just look at the first, say 1 to 6 rows. It's just going to be filled with NAs, nothing in there. Okay. The for loop, basically, we just say, all right, for I equals 1 to n, we're just going to fill each row of that matrix. So we're indexing in the ith row, and when we leave this blank on the side of the columns, it's going to fill the whole columns with whatever we get out of running the simulation, simreg2, which is going to be 2 numbers, the intercept and the slope. You can just run that. Runs quite quickly. Fills it up. And then you can run, if you would like, you look at a histogram of the estimated slopes or whatever. Use exactly as we did before. And finally, I should just let you know that there is a function in the ARM library, associated with the Gelman and Hill book, that actually does simulations, not just for very simple linear models, but as we will see later in the class, we can use it for lots of generalized linear models and even some mixed models, which has a pretty simple interface. Basically, we just call sim, and we call sim with for the name of the model, and then of course the number of simulations we want to do. We do need to run those. It'll just take a sec. And then once that's done, essentially you can grab simulated slopes from it, as we've done here, and compute confidence intervals this way. And just compare them to what we got before, and our confidence intervals are actually pretty much in line. They're not going to be exact because they are Monte Carlo, but they're pretty much in line with what we see before. And we can plot just as we did before if we so choose, which is very much the same. All right, great. Well, thank you, and that's the end of the screencast on using Monte Carlo simulations to generate confidence intervals.